All right, everyone. Thank you for your patience. My computer hates me right now, it seems, this past week. I don't know what's going on with it. Um, Anyways, let's not waste any more time. And let me fix this spacing right here. Boom. There we go. Okay, so Math 162, Week 10, Lecture 1. This is our last meeting. Remember, we said that Thursday, the 29th, this Thursday, will be the day of the final exam. And because we only have one day, I'm not going to teach the same day that we're giving the final exam to make sure that you have the class time to take the final exam. More importantly for today, make sure that you take test 3, which covers the material from chapter 7 and 11 that we went over extensively already. So remember that those test dates were yesterday, the 26th, and today, the 27th. I do not think anyone has taken the test yet, but you should find the test in my math lab. You should find the work submission in Canvas per usual. Make sure you put your name on your work, number your work, turn it in within 15 minutes, like you've all been doing a great job of all summer semester. You'll have 2 hours for the test. It's 20 questions. You are allowed calculators. You can use the formula sheet that we had for test 2, but it's honestly not going to do you any good because none of that material is on test 3. However, you will still want that formula sheet for the final exam, which is cumulative, so the test 2 material will come back up. So the homeworks you have due on the horizon, 11.2 is due today, 11.3 we said is due Thursday. I would say it's a really good idea to go ahead and have those done before you take the test though, since the test is on that material. Again, I apologize for having to cram so many things at the end, but that's exactly how summer semesters work, unfortunately. It's just a product of the shortened semester. So test 3, make sure you take it today. Final exam, make sure you take it Thursday. I will not be able to give any late final exams, so make sure that you take it. There'll be no excuses for that. 28 questions, 3 hours, calculator allowed. Remember, you still need to show all your work, so you'll have a calculator now available for problems from test 1, but if the answer is supposed to be something like square root of 2 and you write 1.41, you just choose the round in the nearest 10th or 100th or whatever, that's going to be wrong. And I'm going to say, well, clearly you didn't put any thought process into this. You just let your calculator do everything. I don't see any analytic work on your work, so you're not going to get partial credit for that. Now, if you did have the analytic work on your work that you turn into Canvas and you point that out to me, I could still give you credit, but I'm not going to give credit for something with no work, just a decimal answer to something that should have been a radical. That is still expected of you. Your calculator could certainly be used to check your answers to things like that, but it shouldn't be doing all of the work for you. So final exam is cumulative. Study, there is a final exam review available in my math lab, but in addition to that, you can go back and study the test 1, test 2, test 3 reviews. You can also go back and study test 1, test 2, and test 3. I can promise you that probably 90% of the questions that'll be on the final will basically come from test 1, test 2, test 3, review 1, review 2, review 3. I'm not really going to pull any punches, so to speak, per usual. Also, please remember that you should be completing course evaluations. They usually email the students about that. I have not received any notifications the past couple semesters. The teachers haven't heard about it. Probably a product of this Zoom thing we're doing. But they're usually in, so check your emails, look for those. We tend to have less students submitting reviews of the course. Hopefully you have good things to say, but if not, be honest, it is what it is. And then we can learn from this and make the experience even better in the future. This is possibly the last or next to last time we'll be doing the Zoom classes as a majority for TCC, but who knows what the future is going to bring, obviously, with variants and such. Life is what it is, but we make the best of it. Hopefully we're able to learn. And I think that this has been a great experience, at least in one way, that you do have videos to replay, and I'm not going to take them down. So in the future, if you're like, oh man, I can't remember, how did we handle the sum formulas and the difference formulas for trig? You can go back and watch the video. It's still going to be there. I don't have any reason to take it down, so why would I? Whereas, the traditional classes, I never recorded anything. If you didn't take good notes, that's it. You'll have to go and find someone else's representation of the topic, which is not necessarily a bad thing. You just wouldn't have had my specific way. So this again will be our last lecture today, and I'm going to keep it short and sweet. We're only going to do about an hour today. We're going to let's see, we're going to cover and finish 10.2, and then I'm going to give just a very, very brief introduction to 10.3, but I'm not going to feel the urge to complete it since it's on parabolas and we've already studied parabolas extensively. This is studying them, or would have been studying them, from a very different perspective, the geometric perspective instead of the algebraic perspective. But the thing is, most future math classes don't really take this approach on parabolas that we're going to, again, very lightly introduce and then just kind of brush past. Most future math classes use the concept of parabolas in an algebraic manner, like you've already previously learned, like you studied extensively in Math 161. I'm not saying that no one ever uses the geometric perspective of parabolas. They're very, in the field of satellite data collection, things like that, they use the more geometric approach. And again, I'm going to introduce that concept very, very shortly in just a bit. We're like 45 minutes or so. But I just don't feel the need, like I've already said 2 times, I like to repeat myself to make sure that everybody catches it. I just don't feel like it's super, super mandatory that we go into this. You're not going to use it in Calc 1. You're not going to use it in Calc 2. You're not going to use it in Calc 3. You're not going to use it in differential equations. It would be something very different that you could study on your own if all of a sudden you got a job working with satellites and you need to understand this idea of everything bouncing, and then no matter what, it hits a certain point, maybe a focus. And then that's where you can collect the data, or if you were sending a signal out, that's where you can send it from. All right, so let's not waste any more time. Let's go ahead and pick up where we left off with chapter 10, and then that'll be it. I'll be in the chat if you have any questions, per usual. Oops, I was so busy trying to get the class up and running, I forgot to pull the video, so give me like 30 seconds, and then it'll be ready. All right, 10.2, the hyperbola. So in 10.1, we studied the ellipse, which was just a wide circle, basically. Now, whether you are drawing it more elongated horizontally or vertically, you can still just say that's a long circle. I know it's kind of a silly way to think of it, but again, it's just like you took a circle and you pulled 2 sides of it and stretched it, whether the 2 sides are horizontal or vertical. In fact, they don't have to be stretched horizontally or vertically. You can also stretch them at an angle. There's nothing to say that you can't have a hyperbola, sorry, an ellipse. And I should do a better job connecting them. Again, this is not a hyperbola, this is an ellipse. There's nothing that says you can't have an ellipse that's drawn like this in a rectangular coordinate system where it's not centered at the origin and it does not open horizontally or vertically. It opens at, say, a 30-degree angle or a 42-degree angle or a 19.7-degree angle. This is when you start getting into rotational coordinate systems, which are a very, very fascinating topic. I would love to teach a second semester of this course and get into that, but we only have so much time, and you only have so many topics that are really mandatory through the calculus sequence. Rotational coordinate systems are a more important topic for advanced math, but not for us. So the hyperbola, what is it? Why should we care about it? How do we deal with it? Well, a hyperbola, as opposed to hyperbole, which is to exaggerate greatly, like your math teacher does sometimes, is the set of all points where the difference of the distances from 2 fixed points, your foci, same type of thing as before, is constant. So an ellipse was the set of all points where the sum of the distances from 2 fixed points was constant. A hyperbola is it kind of feels like the opposite of that. It's the set of all points where the difference of the distance. So an ellipse, it's this same idea, but a sum. A hyperbola, it's the same idea, but a difference. So there's no real rationalization as to why this picture comes out without actually just seeing it experimentally. But if it opens, and I'll say opens horizontally, this is what we end up kind of looking like. And I don't like doing these without the slant asymptotes, and I'll get into what that is in a bit. But this is what a hyperbola looks like. It almost looks like if you took the left side and actually moved it over to the right. And I'm going to erase this in just a second, but it looks like if you took this section and you put it over here instead, it looks like it would form an ellipse, kind of. But these things extend infinitely, whereas an ellipse takes up a very small, relatively small, finite area. So this is what a hyperbola ends up looking like. It's kind of like you took that ellipse and you pulled it so hard that it split at the top and bottom, and then you just said, nah, I want this on the other side and this on the other side. So your foci, and why am I drawing it on the outside? That's silly. Your foci end up being something like here and here. Those are your focal points, your fixed points. We have our center in the center, of course, because we're centered at the origin here. Here's our x and our y axis. Our vertex, let me get a different color. We have two vertices. There's a vertex and here's a vertex. Just like with the ellipse, we had two vertices, which were along the vertical, the vertical in this case, if you, again, reconnected everything. But this is a very different idea. So your vertices are kind of like what would be the sides of a parabola. These are slightly parabolic, but they're not parabolic. There's a reason they have that bola in it, like parabola, hyperbola, because they're similar but different. And then we call the horizontal axis in this case, this is the transverse axis. So the transverse axis is important for a hyperbola in the same respect that the major axis was important for an ellipse. The major axis was where the location of the vertices and the foci would be. The transverse axis is where the vertices and the foci would be. So this is kind of like our major axis. There's no real reason to call, in this case, the y-axis a minor axis. There's no like perpendicular word to transverse as far as I know, so we don't really give it a name. Okay, so this is what they look like if it, quote, opens horizontally, which means it's a horizontal transverse axis, or they could look like this. Let me get my black out. So we're just gonna do both versions at once today. Definitely have a lot less time. Might not get too far into the parabolas. So if they open more vertically, then the vertical axis is transverse. And like I said, these things are kind of like wide parabolas, kind of like wide parabolas. Something like this. They don't have to be that wide, but you get the idea. They are pretty wide in comparison generally. So we have our same vertices at the tops and bottoms of these shapes. So those are our vertices. Our foci are inside of them, inside of the bowl, if you will. And then this time, the vertical axis is the transverse axis. So I want to just very, very briefly put up here the set of all points where the difference of the distance from the two fixed points is constant, so the foci. So say you've got this point right here. Here's our random point. Here's the distance to one of the foci. Here's the distance to the other one. So we can call these D1 and D2. The difference of those is always constant. So, and you can just do always the larger minus the smaller. So d1 minus d2 is constant. That's the idea behind a hyperbola. It's a little more challenging to do like the ellipse in person, where you just, you anchor down 2 points with a string attached, and then you make it taut with your pen and you end up drawing an ellipse. There's no real good way to do that here. So a little more faith. I don't want to say face, a little more faith value. Face value, faith. I think I just combined 2 phrases. That's what I was trying to do on accent. A little more faith involved here, but no matter where you are, the difference of these 2 distance results will always be the same. So if this point right here, let's say the differences were 5. If I were over here at this point, if I was at the vertex, the distance to the left foci and the right foci would be the same value I said, which I think before was a 5. So what do these equations look like? Black. There we go. So for a horizontal transverse, which is above, if we're centered at the origin, and let me say that first. If centered at the origin, and if you have a horizontal transverse, the equation is, and this is going to look pretty familiar. This is going to look pretty familiar, but a little different. X squared over a squared. Hey, that looks familiar. Then to the right of it is a y squared over b squared. That looks familiar. And then by itself on the other side is a 1. Wow, this is the equation of ellipse, right? You just put a little plus and it's an ellipse. They're the same thing. So let's just take something at another, again, kind of a leap of faith, but maybe you'll believe me. When we had an ellipse, we said the sum of the distances was constant. The sum. That looks like a times. It's a minus. Let me make sure that you can see that that's a minus. So again, with the ellipse, this thing right here was a sum, and then in the formula, there was a plus sign between them. Well, maybe that has something to do with when it's a difference, there's a minus in the formula instead. So this is the equation of a hyperbola that opens horizontally. The transverse axis is horizontal. And then A and B would have some type of relation, probably to maybe the vertices. Maybe not. I don't know. Let's see. Let's keep working with this. So, what about the vertical? Again, directly above. So this goes y squared over a squared minus x squared over b squared equals 1. So this looks just a touch different than what we've seen so far. It was always x squareds and y squareds, and with an ellipse, honestly, it didn't matter because it's a sum. You could have certainly written the y squareds before the x squareds. Now with an ellipse, the a's and the b's had to deal with the size of the vertex value. In other words, the larger one gave you the vertex, it gave you the major axis. The smaller one gave you the minor axis, and kind of like a fake vertex, if you will. Just the most outer point on that ellipse. Here, the A and the B have nothing to do with size. Once again, A and B have nothing to do with size, and I'll write that down at some point, sooner than later. A and B have nothing to do with size. Now, there was also a c squared, and the c squared related to the focal points, the foci. There's a c squared for this as well. So for both of these, c squared, and again, kind of, oh, okay, when this was a difference, this is a difference. When this was a sum, this is a sum. The c squared had a sum before. Well, that's probably a difference here. And that's I'm sorry, this was a difference before. Now it's a sum. I think I may have set some signs incorrectly somewhere, but this is a sum. It looks exactly like Pythagorean theorem. It looked similar like to this for an ellipse, but it was a minus instead, which means it's not Pythagorean for an ellipse. So this is the same thing. C squared is a squared plus b squared for hyperbolas. For ellipses, it was a squared minus b squared. Now again, that note that I said, a is not always bigger. That's a bigger than, not a 7, than b. For a hyperbola, the a and the b, the size of them is not going to determine whether it opens horizontally or vertically. It's the sign of the variable term that determines this. Oops, take it off highlight, Rodney. Come on. There we go. The sign of the variable terms determine which way it opens. Okay, so when the horizontal axis was transverse, the x squared term was positive and the y squared term was negative. So the positive term is what tells you which way it opens, because this was a positive x squared, it opens left and right, it opens horizontally. For the vertical transverse, when it opens up and down, the y squared term was positive. So the positive term tells you it opens in that direction. If the y squared is positive, it opens up and down. If the x squared is positive, it opens left and right. That is not anything complicated to remember, but you have to spend the energy remembering it. And guess what students tend not to do? They tend to not spend the energy remembering things, and then when they take their test, they get them backwards, or they just think these are ellipses because they have x squared and y squared. All right, so for example 1, and we're not actually going to get to graph this yet. Let's identify the vertices, the foci, and which way it opens. In other words, which one's the transverse axis? For A, we're going to go x squared over 49 minus y squared over 36 equals 1. Now, your vertices and foci still lie at appropriate points based on which one it looks like. So if it opens horizontally, if the transverse axis is horizontal, then that says these are always going to be the number comma 0, because you're going to go left or right, but not up or down. Okay. So the x squared term is positive here. The y squared term is negative. That means this is not an ellipse, this is a hyperbola, because they're opposite signs. They're on the same side of the equation and they're opposite signs, so hyperbola. The x squared term is positive, so it opens horizontally. In other words, the transverse axis is horizontal. So that says that the number under the x squared is the a. So if you go back into the forms, the a squared this time deals with the positive term. The a squared deals with the positive term, not necessarily the bigger one. So we could swap the 36 and the 49. So if this was a 36 right here, then the a squared would be 36. So a squared is 36. Taking the square root of that tells you that a is equal to 6. I don't know what happened to my 6 there. There we go. That makes the b squared. You know what? I'm about to do the same thing I did last lecture. A squared is not 36. A squared is 49. Good Lord. I get so focused. I'm always thinking 15 seconds ahead. And then I start talking at the same time. This happens more when I'm wearing this silly microphone. A squared is 49, which means A is 7. B squared is the 36. So that makes B 6, taking the square root. Then C squared is supposed to be the sum of the squares, kind of like Pythagorean. So it's going to be 7 squared plus 6 squared. Sure, you could have just gone ahead and written 49 plus 36 if you recognize that, which is 85. So that means c squared is 85. Let's take a square root of both sides to get c equals the square root of 85. Which, if you were to graph this, you would need to know that this is about 9.2. We're not graphing it though, so it is irrelevant for the problem, but I'm pointing it out anyways. So your vertices relate to the positive term. Again, we mentioned that earlier. The vertices will relate to the positive variable term, just like the foci relate to the positive variable term. So your vertices, so that was the 7. So remember, we're going left and right 7. So it would be 7, 0, and negative 7, 0. Your foci would be square root of 85, 0, and negative square root of 85, 0. Hey, buddy. That's my dog, sorry. Not just talking to myself. I mean, I am. I'm talking to you, but talking to myself. I don't feel crazy at all. All right. Thankfully, some people come in the chat every now and then and say something to remind me that I'm not alone. Okay, so I did not ask you to draw this. I just asked you to identify the vertices and foci, which we did, which way it opens, which we did. I'm going to just very small little corner over here. Well, I guess I can put it here. We said it opens horizontally, so it has to look something like this. This point right here, those would be the 7s and the negative 7s. Then the foci are the square root of 85s, which were about 9.2. The reason I did the 9.2 is just so I can do this. So you can see that they're, quote, inside the bowl. So there's the square root of 85 and a negative square root of 85. So the reason I did not ask you to draw this image is because how much we bend this hyperbole, haha, made a joke there, sorry, hyperbola, how much we bend this hyperbola is dependent on the A and the B. So the A not just tells us the location of the vertices, it also has a relation with how much this thing bends, but we haven't gotten there yet. I actually doubt we'll get to parabolas at all, unfortunately. I'm sad. All right, let's do another one of these. Just practicing with the details. Y squared over 36 minus x squared over 64 equals 1. Now this problem I think is important because it demonstrates that the a squared is not always the bigger one for these problems. The a squared relates to the positive term, which relates to which way these open. So the variables are on the same side. They're all being squared, but they're opposite signs. If they're the same sign, this would be an ellipse. They're opposite, so it's a hyperbola. The y squared is the positive term. Because the y squared is positive, this, quote, opens vertically. In other words, the transverse axis is vertical. Now again, the a and the b do not have to do with size for hyperbolas. It has to do with the positive and the negative term. So that tells us, and I'm going to get it right this time on the first try, a squared is 36, so that a is equal to 6. B squared is 64, so that b is equal to 8. C squared is the sum of the squares. I'm just going to go ahead and leave that as 36 plus 64, which conveniently is 100. If c squared is 100, that says that c is 10. So remember, C relates to your focus, A relates to the vertex. So the vertices, now since this opens vertically, it's going to look quite the opposite of this last one. So it's not going to be the coordinates and 0, it's going to be 0 then the coordinate. So 0, 6 and 0, -6. You can put the negative first, nobody cares. So that'll be up and down 6. The foci will be 10, 0 and -10, 0. And that's it. We got how it opens, we got the vertices, we got the foci. Again, as a super quick sketch, this is not an official answer, but just so you have a relation to this, this point right here would be your 6. This would be your -6. And then we have our hyperbolas kind of extending from there. Again, how wide or narrow these are, I'm taking a little bit of a guess here. And then your foci are here at 10 and -10. So again, was not asked to sketch, and this is not a super accurate sketch. In fact, the way that I'm bending on these is technically incorrect. I'm bending a little too much, believe it or not. But let's get into how we can actually do those graphs officially. We were able to currently graph the foci and the vertices, but actually knowing what this shape looks like, we're not quite ready because we need to do something called the box method. Now, and I don't mean the box method for factoring, completely different thing. One last memo. I said there's no like great name for the opposite of a transverse axis, kind of like major versus minor. But when we talk about complex variables, we talk about conjugates, those are kind of like opposites. So for some reason, maybe this stuff relates to complex variables, you know, later in math, maybe. Maybe that's a hint. But we call the perpendicular axis to the transverse the conjugate axis. And we can go back and spell axis correctly. Too many X's. The conjugate axis is always perpendicular to the transverse axis. So for ellipses, we have major and minor. For parabolas, we have transverse and conjugate. Do the names really matter? I think you know what I would say to that. What matters is you understand how they function, how they operate. I can't tell you how many times I have temporarily forgot that these were called transverse and conjugate axis, but I have never forgotten how these things function, how I know whether they open vertically or horizontally, how I find the foci, how we find the A's and the B's for the vertices, or how to do this next box method of graphing. A name is a name, but a method, an application is everything. So the box method, BIX, the box method, graphing hyperbolas. First, find the center, which will not be an issue for us, the A, the B, and the C. Second, plot the vertices, as well as marking what would be the vertices on the conjugate axis. Note, I call these fake verts. They're not actually vertices, they're fake points, they don't exist. We're just gonna mark 2 points where they would be. So the A gives us the location of the actual vertices. The B gives us the location of what I call, quote, fake vertices. So they, instead of going up and down in the last example, they'd be left and right. Or instead of going left and right in the previous example, they'd be up and down. So those are on the conjugate axis, as we say here. Now what you're gonna do is you're going to draw a dotted box around these 4 points, the actual verts and fake verts. Now, you want to make this a horizontal vertical box. So what you might think is, your points are going to look something like this. Oh, diamonds. So some people are going to start, connecting dot to dot directly, dot to dot directly, and they're going to make, kind of looks like a square on its side at a 45-degree angle probably, or a diamond, but no, that's not what I mean. What I mean is you want to have a horizontal/vertical box. I went too far to the right. I went too far down. It's fun not being able to look at what you're writing. There we go. That's what I mean by a box around those. So each of those vertices and fake vertices are the center of one of the sides of the box. This is what you'll be drawing up. Then step 4, you're going to draw dotted lines from the center to each corner and extend. So your center's here. You're going to draw dotted lines from corner to corner, cutting through the center, and extend. That's what I'm talking about. So you're going to draw a box using your vertices. Then, using the corners of that box, you're going to draw dotted lines through them and way past the corners. Not just inside the box, you have to do it outside. These are the slant, I got too many F's above, asymptotes of the hyperbola. So an asymptote is something that pulls a function towards it as you go on forever and ever and ever and ever and ever. We've dealt with vertical and horizontal asymptotes in Math 161. If you came from another place besides TCC, maybe you dealt with slant asymptotes in your pre-calc 1 or math analysis course or whatever, but we don't cover them officially at TCC, even though I think we should, and if we had time, I would cover them with my class. But we don't, and we don't, so I don't. So a slant asymptote just means instead of it, pulling you almost directly up or directly right, it's gonna pull it kind of up and right or down and left, depending on where you're coming from. So you draw your shape from those vertices and then bend towards the slant asymptotes. So let's say we were drawing this first one. So I drew my little box using the A's and the B's. I drew my slanted lines. So let's say, give me blue. Let's say these were our real vertices. We're going back to the first example. Then you draw that kind of bending, parabolic, elliptical looking shape, but the further right or further left you go, the closer you're going to get to these slant asymptotes, something like this. And that is how that shape ends up being made. And this is one of the more challenging things to get used to drawing in math, admittedly, and we don't have very much time to do so. But that is how you draw a hyperbola. Now, in my math lab, obviously you're not going to be doing that stuff by hand. You have to get your A's, B's, and C's, and then it gives you a way to make that in my math lab. It's fairly reasonable in how it gets that done, thankfully. But coming out of this class, you need to, in theory, understand how to do this by hand. Now, you won't really see a lot of drawing hyperbolas in Calc 1. You won't really see a lot of drawing of hyperbolas in Calc 2. You don't necessarily see them in, say, differential equations. This is just something that comes up occasionally in advanced math that is good to have seen before. But it is really just a formula and a series of methods to graphing something. So we feel the theory is, even if I didn't teach this to you, we're all supposed to be educated enough to be able to get this down in, say, 20 to 60 minutes, even if you never saw this and all of a sudden your Calc 3 teacher decides to have a hyperbolic lecture, pun intended. So let's go back to example, do I want to redo it? No, I'm going to do a new one. Example 2A. Let us find the vertices, find the foci, and then graph. And this is x squared over 49 minus y squared over 64 equals 1. X squared over 49 minus y squared over 64 is equal to 1. Okay. You have squared terms, so it's probably an ellipse or a hyperbola. But they're on the same side, and one of them's a negative, so that means it's a hyperbola. The x squared term is the positive one, so it opens left and right. It opens horizontally. It's a horizontal transverse axis. It opens horizontally. That's the way I really like to say it. You know, who cares about the name transverse axis, right? So the a and the b have nothing to do with size. It has to do with positive and negative terms. So the a squared should be the 49 then, which makes a equal to 7. The b squared is 64 then, which makes the b 8. The c squared is the sum of the squares. So 49 plus 64, which is 113. So c squared is 113, meaning that c is equal to the square root of 113. So our vertices. Remember, this has to do with the positive term. The x squared was positive, so the 49 has to do with the vertices, so that's the 7s. So we're opening horizontally, so we're making sure that we're going left and right, so this should be 7, 0, and negative 7, 0. If you swap the zeros and the 7s, they'd be going up and down to get those, but we're supposed to open horizontally, not vertically. The foci, that relates to the c, that's going to be square root of 113, 0, and negative square root of 113, 0. So let's start drawing this bad boy. Black. We're opening horizontally, yes. So might need a little more room this way. Might. All right, so the A was on the x-axis, so we got to go left and right 7. I'm not going to mark every single number. There's our negative 7. Here's our positive 7. The B squared was 64, so the B is 8. So we're going up and down 8 to get those. In fact, I don't want to have those so far out on my graph. Let me squeeze them in a little bit more. Here's my negative 7. Here's my positive 7. Here's my 8. Here's my negative 8. So our actual vertices are here and here. There will be fake points on the 8 and negative 8 in just a second. So there's going to be fake points. So I'm going to do them in, let's go yellow. So a little fake point here and a fake point here. So that's a fake point. This is a fake point. This is just for the box method. So find the center A, B, and C. Plot the vertices as well as marking what would be vertices on the conjugate axis, the fake vertices. So the red ones are the real ones, the yellow ones are fake, they're just important for the box. So now let's draw up our box. Yeah, blue's fine. So I mean, you can technically make this a solid box if you want, but you might then think it's part of the graph. Nobody wants you to think that. So there's our box, and then you just make slanted lines going from corner to corner, making sure you're cutting through the center. Do this as best as we can. It's going to be crappy. better. Good enough. There are our slant asymptotes. This is what will pull our function to as we go further left and further right. So we'll do the actual graph in red. So now we just draw that kind of bowl-like shape, but the further we go right from the +7 or the further we go left from the -7, the closer we get to that slant asymptote. So something like this. And there we are. There is our hyperbola. There is one detail that we have not described yet. I wanted to get the graph first. I didn't want to throw everything at you all at once, but that is how you can get a graph of these by hand. Is this the most accurate depiction in the world? No, you could, plug in some X or Y values to find actual other coordinates if you wanted to really make sure that you've got this thing bending correctly. But this is good enough. This really is good enough. It's not a function, just like ellipses aren't functions, but it's still an equation of a very important description of shapes. Changes. So what's the last detail that I meant? Well, that I've said we haven't talked about? Well, these dotted lines, these are equations of lines. Guess what? We can describe equations of lines with a couple of points. Now, you can use this point right here, 7, 8, and this point right here, 0, 0, and then get your slope and then use point slope method. Y minus y1 equals m times x minus x1. You can do all that jazz if you like. So again, you have they're going through the origins, that's 0, 0. It's going through 7, 8. So you can find the slope, which will be 8 sevenths. The change in the height over the change in the horizontal. And then you can go y minus 0 equals 8 sevenths parentheses x minus 0. You can distribute, and then you end up with the equation. And then the same thing would happen for this one that's going down, because there's two lines, there's two equations. What it ends up turning out to be is y equals 8 over 7x, and y equals -8 over 7x. That's the equation of the equations of those two lines. I'll show you the derivation of the top one. You have the point 0, 0 and 7, 8. So the slope is 8 minus 0 over 7 minus 0, which is 8 sevenths. And then let's just use this point and the slope. So y minus 0 equals 8 over 7, parentheses x minus 0, which is just y equals 8 sevenths x. So that works. The same derivation can be used to find that one. Here's something cool though. You don't have to do all this work if you do pattern recognition. The 8 and the 7 were the A and the B. So the slope of this line is always going to relate to the A and the B, and it's always just going to be y equals a number times x, where these are the A and the B. Now, they change depending on whether it opens horizontally or vertically, which one's on top and which one's on bottom. But guess what? The y value, the y point that you have for your fake vertice or real vertice is always the top one. The x value is always the bottom one. It's always the y value over the x value. It's always the y value over the x value for your slope. Again, that orange stuff is nothing new. You should have seen that in 3 different math classes by now. I am not reteaching equations of lines. You were taught them 3 years ago, 4 years ago, 5 years ago. You're supposed to remember them forever in theory. We do reintroduce it in pre-calc 1, so that's really just a semester ago. But there they are. That's everything. So our slant asymptotes, let's officially write this down now that we've applied it. If it opens horizontally, the lines are, and then if it opens vertically, the lines are, So if it opens horizontally like we just saw, it's y equals plus or minus b over ax. But if it opens vertically, it's y equals plus or minus a over bx. And that's just relating to this, the y value over the x value. The a's and the b's swap depending on which way it opens, because that had nothing to do with size. So I don't actually remember it this way as a over b or b over a, because you've got two sides of a coin. I remember it by crossing out part of the important bit. I remember it this way, that it's always the y value over the x value, because slope is always rise over run. And if we're centered at the origin, it's always going to rise based on the y coordinate and run based on the x coordinate. So again, we had the equation. We knew it was a hyperbola because opposite signs, and they're on the same side. So the A dealt with the 49, the B dealt with the 64, had nothing to do with size, had to do with positiveness. The C squared, sum of the squares, take the square root. Label the vertices, label the fake vertices, box around those, slanted lines cutting through those, give those equations, and then draw your hyperbola. Let's try another one of these, and this might be our last example. Let's see, B. That's fine in red, but let's make it black now. Draw. Humana. And let's mix things up just a touch. 4y squared minus 16x squared equals 64. Hey, Mr. Beckner, that's not a 1 on the other side. I don't see fractions. This isn't an ellipse. This isn't hyperbola. Oh, yes, it is. We had an ellipse problem like this. You just had to divide everything by that number on the right-hand side. Same thing here. Divide both sides by 64. So divide by 64, divide by 64, divide by 64. And what that gives us is going to be y squared over 16 minus x squared over 4 is equal to 1. Now we have our hyperbola. So the a squared will be the 16. So a is equal to 4. The b squared is equal to 4, so that b is equal to 2. C squared is the sum of the squares. Not 16 squared, just 16. Plus 4, which is 20. So if c squared is 20, c is the square root of 20, which is going to be 2 squared is 5. Because 20 is 4 times 5, square root of 4 is 2. Now, we'll need this approximation for graphing. It turns out that's about 4.5 if you type it in a calculator. This thing will open vertically, not because of the size of the a or the b, but because the y squared was the positive term. Because it opens vertically, you're going up and down. That says your vertices, which are based on the a, will be 0, 4, and 0, negative 4. The foci will be based off the c, so 0, 2 square root of 5, and 0, negative 2 square root of 5. And let's go ahead and identify our slant asymptotes. SA, slant asymptote, it's y equals plus or minus some fraction of numbers times an x. So this is representing a fraction. And these are just the b and the a. It's just a matter of which goes on top and which goes on bottom. Well, the 4, which is the a, related to the y squared. So the 4 relates to the y, so the 4 goes on the top. The b related to the x squared, so the b goes in the bottom, and that was the 2. But 4 divided by 2 is 2, so y equals plus or minus 2x. Those are the equations for these slant asymptotes. So that is the thing that these will gravitate towards as you go left forever or right forever. So here's what's cool is with that, if you know how to graph 2x and negative 2x, you don't actually have to use the box method. You can just plot those lines and everything is going to be perfect. But I still like to use the box method personally. So we're going to open vertically. Give myself a decent amount of space. So once again, the vertices, the real vertices with the 0, 4 and the 0, negative 4. So let's put them maybe about here and here. So there's our vertices. These are real points in red. The fake vertices along the conjugate axis, those were the 2's. So we'll go right 2 and left 2. Those are fake points. So write fake somewhere, use a color, whatever you have to do. So those are fake and fake. And then we draw our little dotted box around this. I'll do that in blue. And then corner to corner and extend them. This is so hard to do this way. I really miss seeing y'all in person. I miss my whiteboard. I miss it all. There we go. So this top one is y equals 2x. The bottom one is y equals negative 2x. If you don't know why that is, you're terrifying me right now. And then we draw our hyperbolic shapes. So kind of bendy, kind of bowly, but tending towards these slanted blue lines as we go forever. And we're drawing them from the real vertices, not the fake. Those orange points, I don't even need them anymore. I could erase them now if I wanted to. It's probably a bad idea for note taking. So something like this. And if this was a by hand test, I would not care how quick or slow you ended up super close to that asymptote. This right side is not perfect, admittedly. It is what it is. The left side is a much better representation. Same there. The left side just looks a little better. I can probably do a little better than that. I'm going to try one more. Keeps. There we go. And there's our graph. There is everything we need to know about the hyperbola. So we've got about 5 minutes left. I'm going to cut it there for hyperbolas. Again, you've got some homework problems that you can tackle in 10.2. You are not going to do all those problems. And again, I am exempting the grade. It will not hurt you if you don't do any of them. I do not have a specific number of problems that will be on the final. I'm thinking in the ballpark of 30. No less than 25, no more than 35. I can guarantee that. If I had 35, there'd be a lot of small problems. But I'm thinking 30 is going to be the magic number. 28, 29, 30, somewhere around there. So not significantly longer than a regular test. And if you remember test 1, we had a lot of short questions. Basically, I'm going to be pulling problems from test 2 and test 3. So the review for those and the tests for those will be very good to study. I'll pull similar problems to test 1, but they're going to be a little more similar to the MyMathLab format because I'm making a MyMathLab test. So I'm not going to give you any problems that's just, hey, what is sine, opposite over hypotenuse, or anything like that. So none of the super, super ridiculously simple stuff, but still some simple questions as well as more complicated questions. So parabola, just before we move on, which is 10.3, the forms of these is y squared equals 4 times p times x. I will not give any parabola questions on the final. I reserve the right to give you an ellipse question and a hyperbola question because we have officially covered that, and they would be no more advanced than what we've done in the lecture notes. So if you can handle the lecture note problems, you can handle what you'll see on the final. So again, this is just something I feel the need to show you, to relate to. So y squared equals 4px. This opens horizontally. It has a focus. Since it opens horizontally, that would be p comma 0. There is no second focus for these. And then it has this thing called a directrix, which is the line x equals negative p, or it's x squared equals 4py. That's when it opens vertically. Then the singular focus is 0 comma p, and the directrix is y equals negative p. So those two cases, it opens horizontally. Remember, parabolas, you just get one of them. It's not like the hyperbola where there's two, you just get one. So this is an open horizontally. Here is our P, that's our focal point. And then the directrix is a vertical line that is opposite to that. So that point right there, that's x equals negative P. So the distance from the vertical line to the center is the same as the distance from the center to the focus. Or if it opened vertically, which we are much more used to, then here is your P, and then it's a horizontal line that's y equals negative P. So this is the geometric version of parabolas. And a parabola is the set of all points that are the same distance from a fixed line and a fixed point. So what we're saying here is, and I'm only going to do it on the right one, this point right here, this distance, and it doesn't look like it, but those are supposed to be the same. This distance is supposed to be the same as this distance. But I'm a bad artist, so it does not look exactly the same, but they should look exactly the same. So parabolas are built such that the distance from the parabola to its focus is the same as from the parabola directly to a vertical or horizontal line behind it. Parabolas are fascinating, they're amazing, they're used all over the world. Anything having to do with satellites, those are parabolas to make sure that we can collect a signal from the center of the dish, the focal point, and then read it from somewhere else. So you have all these signals coming directly at the bowl, and then they'll bounce in the bowl and they'll all collect at this singular focal point. Again, I will do nothing about parabolas on the final exam. Likely we'll have one question that's an ellipse, and likely we will have one question that is a hyperbola. So expect one of each of those. Besides that, the test will be split pretty evenly into test 1, test 2, and test 3 material. Again, some sorry for that delay. I had to get my dog to stop making a bunch of noise. All right, so like I had said, that's where I was going to cut us off. So just up to 10.2, not expecting any more than one question from 10.1 and 10.2 each. But then besides that, the rest of the final exam will come from questions across test 1, test 2, test 3 material. Shouldn't be any surprises. We have our reviews. We know what homeworks are due. We know we got to take test 3 today. We got to take the final on the 29th. There will be no class on the 29th, like we've talked about. Don't forget your calculator. Don't forget your formula sheet for the test 2 for the final exam. That'll be very, very helpful. Besides that, per usual, if you have any questions or confusion, you can hit me up an email. I hope this has been a decent learning experience. Don't forget to do your course evaluations. Check your emails for those. If you don't see them, I'm not sure exactly where they are because they haven't told us anything this summer. But yeah, I wish you all the best of luck in your future math classes as well as everything else. And hopefully you'll be able to use some of this. Hopefully it's not just throwaway knowledge. Yes, there is a final review. It should be in my math lab already at the very bottom of your assignments, the homework section of the assignments. Yeah. All right. So it's been a fun summer. I hope y'all take care. I wish you the best of luck. Finals, future, everything. Take it easy, everybody.